Today he's going to be presenting on battery-free eye tracker on glasses. Please, Qianqing, take it away.
Okay. Thank you for the introduction. Photodiode-based eye tracker. They use low-cost and small photodiodes to track our eye movement. The main issue is that they are not pretty accurate, which is not good for many mobile health applications. And recent work has tried using the specialized man-based lens to improve the tracking accuracy. But the problem is that this specialized lens is very expensive. And so far, there's no existing method that can achieve both high pupil tracking accuracy and battery-free. So first, let me show you the design rationale. Well, the rationale is actually based on the pupil's light absorption property. Here, when we emit light to the eye, our pupil will absorb the light, while all the other part can reflect the light. So if we place multiple photodiodes around the eyes, these sensors can capture the spatial patterns around the eyes. For example, it can capture the patterns when we move the pupil or during the pupil dilation. So here I just show you that it is possible to use a few low-cost photodiodes to track our pupil movement. But the challenging part is that it is still pretty hard to find a balance between the energy consumption, the pupil tracking accuracy, and the tracking rate. As I just show you that the main issue for the photodiode-based method is that they are not very accurate. Well, to solve the problem, we propose two design components. First, to improve the tracking accuracy, we use multiple near-infrared LEDs around the eyes to increase the number of features we can collect from the eye. And to improve the energy efficiency, we adapt the sensing rate based on the eye movement. So first, let's talk about the sensing with multiple near-infrared LEDs. So here we have a ring-shaped light sensing unit. It has 6 near-infrared LEDs and 12 photodiodes. And as you can see, we use a color bar to represent the reflected light change with a center pupil. And by emitting light from different directions, the photodiodes can capture different spatial patterns. And these patterns increase the number of features we can get from the eyes, given the pupil position and size. And actually, when the system collects the raw data, it will first pass the data to a supervised learning models based on the boosted regression trees. And the model will then output the pupil position and size. And next, to improve the energy efficiency, we adapt the computation and sensing rate based on the eye movement. Well, in general, there are 4 types of eye movement: fixation, smooth pursuit, blink, and saccade. Well, fixation is the stage when the pupils focus on a single point with little movement. So the movement during fixation is predictable. Smooth pursuit is an eye movement that follows a smooth trajectory with a relatively low acceleration and a constant velocity. So it is possible to predict the movement during smooth pursuit. Well, for the blink, since the pupil will be covered by the eyelid, so we don't need to track the position and the size for the blinks. And finally, for the saccade, it is a rapid eye movement with very acceleration and velocity. So it is pretty hard to predict the movement during saccade. Well, actually, when we read something or watch something, our pupil moves in jerks. The actual eye movement is a series of fixation points with saccade and smooth pursuit in between. And more importantly, only a small portion of eye movements are saccade. And to verify this, we did a simple user study with 10 participants. And in the study, we asked the participants to perform these 5 activities: slow reading, fast reading, play video games, watch movies, and do conversations. And we use a Tobii eye trackers on the laptop to capture the eye movement from the user. Now on the right-hand side, we summarize the result in a pie chart. As you can see, almost 90% of the eye movements are either fixation or smooth pursuit, and only 10% of the eye movements are saccade. Actually, we observe that even when the users are like playing video games like Fortnite or PUBG, or like watch some movies, the saccade still takes less than 15% of the total eye movement. So it shows that most of the eye movements are predictable. And this result is also aligned with the existing literatures on eye movement pattern. So next, I'm going to show you how we adapt the sensing rate based on the eye movement. So here, the system starts with sensing the reflected light from the eye, and then it uses the sensing data to predict the eye movement into the 4 classes. So basically, the system will just use the past movement trajectory to do the prediction. And for the sake of time, please refer our papers for more detail about the prediction algorithm. So here, the blue arrow represents the actual sensing frames. Now, when the system detects a saccade, since the movement is not predictable, the sensing rate is just equal to the tracking rate. And for the blink, the system will sleep for 200 milliseconds and then wake up. For either of the fixation or smooth pursuit, the system will adapt the sensing rate and interleave some predictive inferences so that the final tracking rate still remains the same. Now here, if the system detects a fixation, it will first adapt the sensing rate to a quarter of the tracking rate in the first 200 milliseconds. And then it will increase the sensing rate to half of the tracking rate. Now the right arrow here represents the predictive inferences. And for the fixation, the inferences is just the purest pupil status. Well, the intuition behind the strategy is that if the fixation remains after 200 milliseconds, it will be more likely for the pupil to exit the fixation. So the system needs to capture the moment timely. And for the smooth pursuit, the system will just adapt the sensing rate to half of the tracking rate. And here, the predictive inferences is computed by the purest 2 pupil position. So that's the end of the design. And next, I'm going to show you the prototype. Well, our prototype is built on existing eyeglasses. It has a microcontroller on the left arm, a light sensing unit that has 6 near-infrared LEDs and 12 photodiodes. And it has 2 small solar cells to power the entire system. So next, let's take a look at the performance. Well, first, to get the ground truth data, we attach a Pi cameras in front of the glasses, and we use the existing Pupil Lab API to pre-process the images, and we ask the user to manually label the data. For example, label the pupil center and size. And in the evaluation, we have 22 participants with different eye color and skin color. And for each participant, we collect 5 minutes training data from them to train a model, and then we ask them to perform these 5 activities to test the system. So these 2 figures shows the tracking performance. The upper one shows the CDF of the pupil position error, and the bottom one shows the CDF of the pupil's diameter error. And in the upper figure, we also compare the tracking performance between our system and that without adaptation. So clearly we can see that the adaptation algorithm doesn't degrade the system performance. And overall, our system achieves about 0.8 millimeters mean error in tracking the pupil position and 0.3 millimeters mean error in tracking the pupil diameter. And this performance is close to the most accurate camera-based method. Now here is the demo video. We just overlay the ground truth and our inferences on the video. The red one is the ground truth and the yellow one is our inferences. And next, we measure the power consumption versus the harvest power. Here, the x-axis shows the different activities, and y-axis shows the corresponding power consumption. Well, on average, our system consumes less than 400 microvolt power. And we also compare the power consumption between our system and that without adaptation. So we can see that the adaptation algorithm consumes about 48% of the power. Now here we ask a user to wear our glasses and perform 3 different user activities in 4 different room settings to measure the harvest power. Now here the x-axis shows the ambient light conditions and the y-axis shows the harvest power. And this figure shows the harvest power during daytime, and this one shows the harvest power at night. Now, as you may see, in some cases, for example, the setting 3 at night, the harvest power is less than the power consumption. Well, the system has a supercapacitor that can store the additional power to support dark scenario. So, for example, if we can, after 1 hour normal usage in the setting 2 during the daytime, the additional power can support the 1 hour normal usage in setting 3 at night. And on average, our system can harvest about 450 microvolt power. It's larger than the power consumption, so basically the system can run forever. And finally, we compare our system performance with the existing literature. And here the x-axis shows the mean pupil tracking errors in millimeters, and we use the energy consumption per gauge tracking inferences to make a fair comparison between different systems. Now these 3 dots shows the camera-based method, and light gaze is a photodiode-based method, and this is ours. So as you can see, the tracking error is close to the most accurate camera-based method, but it saves several magnitude of the energy. Well, there are still some remaining work for the system. So first, the system still need attached cameras on the glasses to get ground truth data. And to solve the problem, we can try using remote cameras, for example, phone cameras, to get ground truth data. And second, currently the system doesn't support outdoor scenarios. The main issue is that in outdoor, our photodiodes can be easily saturated. One of the solutions could be that we can try adapting the gain of the photodiodes by using adaptive amplifiers. And finally, we are interested in studying applications in AR and mobile health using the prototype. And with that, that's all for my talk. Thank you.
All right, Tiancheng, thanks for a great talk. Let's give him a round of applause. All right, our next talk comes from none other than Shivan Banerjee. Shivan, as most of you know, is a professor at the University of Wisconsin-Madison, and his student will also be presenting later in the talk as well, as he will show Chuhan Gao. This is a really interesting work on using new kind of interactions for VR devices, and Shivan will tell us all about it now.
So good afternoon, everybody. I'm Shivan Banerjee from University of Wisconsin-Madison. I'm really nervous because this is actually my first time I'm speaking and presenting a paper at MobiCom. My students have had the luck all the time, and unfortunately for Chuhan, because of his work commitments at an internship, he couldn't make it. So the work really was done by Chuhan Gao and Xinyu Zhang, who's a professor now at UCSD. And I think I'll try my best to be Chuhan, but he would obviously do a great job at presenting this. And so he will actually join us virtually for a bit during the presentation, so you'll get to see him at least. So I'm going to talk about this system that we have been working on and developing called Inkput, which is basically a conductive printed passive 2D trackpad for VR interactions. So I believe all of you are familiar with virtual reality systems, and in particular mobile-based virtual reality systems, where you have a phone, for example, that you put in, say, a Google Cardboard or a Daydream system, and you mount it on your head, so it's a head-mounted display, and then you can do the usual VR interactions. And it's kind of very popular, it's low cost, and it's very effective way for doing certain VR applications that are getting very important these days. So if you think of how you interact with such VR systems, there are multiple ways that one can do this today. One example of this is to use a clicker kind of a device which lets you click and make inputs to the VR system. You can also use a camera-based mechanism that tracks, say, your hand motion and detects what actions you want to do or what inputs you want to provide. And then there are also handheld controllers that sort of do the same thing. While all of them are very effective, I would claim that they are not as low cost as we are looking for in terms of a solution. And as you'll see in the input system, you can probably do some other interesting designs that are useful in this space. So what is input? Let me give you a very quick overview in this slide. Essentially, we print a passive conducting material on photo paper and attach it to the touch screen's edge and wrap it around. So essentially, the back of the mobile device becomes your input substrate. And by touching that piece of paper at different positions, you are able to imitate the actions of touching the screen. The screen, of course, is facing your eye, and therefore you cannot really touch it. So the back side of the device is available, and that's what you touch to provide all the interactions. So it's a very cheap solution, to be honest, but it still works remarkably well. How cheap is this system? So if you think about regular home inkjet printer, itself very low cost, and you can buy the ink at a very low cost too, say $100 for a 50 ml bottle of the ink. Paper is normal photo paper. In the US, you can probably get them at $20 per 100 sheets of this paper. And so if you think of each input interface, it's less than $1 on average. So very affordable, very cheap, easy to put up, and all you need to do is to print this paper, stick it to the end of the touch screen, wrap it around, and there you have your input interface. So I described this casually, but there is a lot of hard work in actually realizing it. The challenges include figuring out how to do the 2D localization of where you're touching on the interface of this paper. Then also to be sort of compatible to how you use a mobile device, you may be interested in multi-touch. So we look into multi-touch interactions. And then another very important capability is hovering. That means you sort of hover your finger on top of the location you want to touch, and the system, if it can provide a visual input to the on the screen or to the eye, saying this is where you are roughly hovering, then the user can more accurately touch the right point that the user is interested in, because you're not actually able to physically see where your finger is touching, but with the hovering, you can actually get a cue, and that helps you improve it. So these are the main challenges this work tries to address. So to give a little background on how this system works, it's useful to think of how these touchscreen systems actually work today. Most of these touch screens that we use are essentially use a form of capacitive sensing. You can imagine the screen is split into various zones of touch, or you can identify touch of an individual zone by the location of touch and by looking at the capacitance of and the capacitance and the discharge of a capacitor that can be modeled for each zone. So if you think of each of these zones, which we will call electrodes, they can be modeled through a circuit. Okay, the circuit is shown in the slide. You have a fixed supply voltage. You have a voltage of the inner capacitor, and then the finger introduces additional capacitance. Okay, and the additional capacitance introduced by the finger changes the time it takes for the inner capacitor to charge. And by looking at the time it takes for the inner capacitor to charge, you can detect the presence of a touch. So that is sort of the basic principle of how touchscreens work today. And this voltage is supplied frequently, and every time it's checking whether the finger is touching the screen or not by looking at the charging time for this duration, for each of these periods. So the most mobile phones would give you a way to access this information. But if you modify the kernel, you can actually get access to the raw data, which gives you more direct access to sort of the equivalent of these charging durations. And for example, Android gives you access to, through its controller, values which correspond to where your finger might be touching the screen. So this is an example where there are different values corresponding to these different electrodes, and high values correspond to the location where a touch is detected. So higher the value, the higher the probability that the touch is there. Lower values means there is no touch at that point. So if you're multi-touch, you will see higher values at different locations. Okay? So this is refreshed frequently, and so you can continuously detect presence of a touch as you're doing any action of input there. So what we do is when we add this passive conductive paper to it, so we have to basically detect the location of touch in 2 dimensions, x and y, right? So the way we do, say, the y dimension is when we touch the conductive material at some point, the corresponding edge of the touch screen, the corresponding row will have higher values, right? So that sort of gives you a hint that by looking at the values when we touch the piece of paper, we're looking at the values of the y dimension of the edge, you can detect what y location is getting touched. So that's sort of the first thing to know for determining the touch point. And then we will have to also determine the x location. So what happens is we looked at this sort of circuit diagram of the touch screen itself. Now when you touch this piece of paper, the x location is sort of related to sort of a resistance that is added to this circuit, and depending on how far you are touching on the x dimension, the resistance is altered. So you can imagine that this material has some resistance, and by touching at a certain point, you increase or decrease the resistance, and that also manifests itself in the touch value that we can get. Okay, so effectively, what happens is, so the modified view of this circuit model that we have is essentially adding an extra resistance that alters the way we can measure the charging time. So these are the 2 dimensions that we need to detect, and from that we get the xy location of where a particular touch is actually happening. So of course, we first had to validate this model through simulation. So we used this model, we checked what is the predicted amount of charging time based on the resistance that you get, and the resistance is varied by moving your finger at different positions on this stripe that we are touching. And on the left side, it shows the estimated charging time for different values of resistance, and you can see that it at least predicts a one-to-one relationship. So that means you will not get confused if there are multiple positions you touch, because there is only one value corresponding to it. And on the right side, you see sort of the measured values that you get from the touch screen, and it sort of follows the model. So we are pretty comfortable with that match in the model and what is measured. And in the system, you have to learn this curve. So you have to do this once for the device to make sure that you know for what value of the touch screen, what is the position that you're touching on the piece of paper that is stuck to the back. Okay, so that's sort of the idea that we have to estimate the positions. There are a few more details. In order to do multi-touch, we have to actually kind of do a little more work because multi-touch manifests itself a little bit differently. And effectively, what we can imagine is if you touch n positions, it will create a matrix of values on the screen, and we have to sort of solve it for the best possible locations you would have touched that led to the matrix. So we use an optimization framework which tries to minimize possible error and comes up with a solution for multi-touch. Okay, so that's details that are available in the paper. And then for hovering, we also leverage a phenomenon which is capacitive coupling through the air. And we have to distinguish between a hover and a touch. And it turns out that the pattern of touchscreen values is slightly different between a hover and a touch, and that lets us distinguish between these two things. So with that, I will
evaluation. We first validate.
With that, I will essentially let Shuhan tell you about the experimental validation and the results he has done, and that's Shuhan, and I will let him speak for this part of the talk.
In our performance evaluation, we first validate the detection accuracy of a single touch. The heat map shows the average touch positioning error on the passive stripes. As we can see, the mean error is only around 2.5 millimeter, which is even smaller than the fingertip contact area. In this particular experiment, similar level of accuracy can be achieved in multi-touch use cases. Here we have 10 users draw along the ground truth curve patterns displayed on the screen, using 3 fingers at the same time. The figure on the left is an example of the detected trajectories, and in our user study, the mean error with 3 simultaneous touches is only around 3 millimeter, and is consistent among different users. On Nexus 5 and Galaxy S5, Hoover detection error is also sub-centimeter level. In our experiment, the user uses a single finger to hover above the screen. The average accuracy on Nexus 5 and Galaxy S5 are around 6 and 5 millimeter respectively. The accuracy actually depends on the sensitivity of the touchscreen hardware. Galaxy S5 is designed to be able to detect hovers, which they call pre-touch sensing. With all the features that Inkput can provide, we present a few use case studies. Here's a mobile VR application example, where we display an object, in this case a bird, and have the user capture it by clicking on the back of the HMD on our printed stripes. One key feature we provide is hover detection. The orange circle indicates the detected hover position and is displayed on the screen. It serves as a hint for the user before he actually touches the back of the HMD. This can help reduce the unintended errors in mobile VR applications significantly. The figure shows the detected touch point cloud with and without hinting with hover detection. The left 4 figures indicates that the users are generally unable to touch the intended target accurately when he cannot see his fingertip on the back of the HMD. But with hover detection, the users are now able to touch the target much more accurately. Here's another example of a new mobile VR application that can be enabled by Inkput. Previously, mobile VR requires the user to rotate his head to move a cursor in order to type on a virtual keyboard. But with Inkput, the user is now able to type on the virtual keyboard in the same way as typing on an actual touchscreen directly. Similarly, the orange circle is the detected hover position, which is displayed in the VR application. Finally, the application enabled by Inkput goes beyond mobile VR. It can serve as a general-purpose solution to extend the interaction area of mobile and IoT devices. For example, it can be used to extend the touchscreen of a smartphone, serving as a paper keyboard. The extension is simply a piece of paper that can be fit into a smartphone case or a screen cover. When not being used, it can also be folded. It also has the potential to service future IoT devices without large touchscreens, making the interaction much easier due to its flexibility and support for easy customization.
So, in conclusion,
through the Inkput design, we have demonstrated the feasibility of expanding the interaction area of a smartphone using a simple paper-printed extension. The paper interface only occupies a tiny edge of the smartphone, but through proper design of the printed conductive patterns, along with careful processing of the touchscreen signals, Inkput can achieve sub-centimeter level precision when sensing multi-finger touches on the paper extension. Our prototype implementation verifies that Inkput can be extremely low cost and incurs minimum detection latency. Our user studies on actual VR applications also demonstrate that it can approach the usability of an actual touchscreen. We believe that Inkput can enable new interaction modalities for both mobile VR and future IoT devices.
Thank you for your attention.
Next, we have Bohan from AT&T Labs Research. He's going to be telling us about this collaboration with Indiana University that they've been doing on this work called Flare. As you know, we have a lot of 360-degree video that's coming out. You see it on Facebook. How do we get this to all of our devices? Tell us how.
Okay, thank you, Robert, for the introduction. Good afternoon. Today, I will present our recent project on 360 degrees video streaming for mobile devices. As Robert mentioned, this is joint work with Feng Qian and Qiang Xiao from Indiana University, and my colleague Vijay Gopalakrishnan. Feng is now with University of Minnesota. So as shown in this figure, 360 videos capture the entire panoramic view. And they became increasingly popular on platforms such as YouTube and Facebook. Differently from the streaming of regular video, when watching 360-degree videos, the viewers can consume only the content within the viewport, which is determined by the field of view of the head-mounted display if the viewers decide to use the head movement to change the viewport. A key concept here is projection, which is the transformation of the image from the sphere to the plane. So in terms of the streaming, currently most content providers take a viewport agnostic solution that delivers the entire panoramic frame. You can view it as a combination of the black box video streaming solution for incremental deployment, plus the projection at the client side for rendering and display. Given that viewers can consume only content in the viewport, this viewport agnostic solution is not network friendly, and it significantly wastes the bandwidth. So to solve this problem, we propose a system called Flare with a goal to improve the quality of user experience and network efficiency. The high-level idea is simple: viewport adaptive streaming. In this figure, we show a video trunk with multiple frames, and we spatially segment the video into multiple chunks and show a 4x6 segmentation with 24 tiles. So this segmentation enables delivery of portions of the video to the user. So the foundation here is the accurate prediction of the future viewport. Our performance evaluation demonstrates that with viewport adaptive streaming, Flare can improve the video quality by up to 18%, and at the same time reduce the bandwidth consumption by up to 35%. So I will use this animation to give you a better understanding of how viewport adaptive streaming differs from viewport agnostic solution. As I mentioned before, for the viewport agnostic solution, the players fetch the entire panoramic frame, and then according to the current viewport, the player will display the content in the field of view. For the viewport adaptive solution, we segment offline the video into multiple tiles, and after predicting the viewport, the player fetches only tiles overlapping with the viewport, decoding them, and then render them for display. So, of course, to increase the robustness of the system, the player can also fetch adjacent tiles. We are one of the first group to propose the viewport adaptive streaming for mobile devices back in 2016, and we have seen lots of papers published in the past 2 years. And here I will briefly discuss two related works that actually build the real system. Rubicus was published in MobiCom this year. Differently from Flare, it requires modifications to the video encoding. BS360 was another paper published in Infocom this year. The issue is that the viewport prediction is missing from its design and implementation. You can refer to our paper for more related work and how Flare differs from them. So although the concept is simple, there are several research challenges when realizing this solution for mobile devices. The first challenge is on the accurate prediction of the future viewport. we have designed lightweight and accurate machine learning-based algorithms by leveraging the data we collected during our user study. Another challenge is on the rate adaptation, which determines the best video quality. So differently from regular video streaming, for Flare, we need to consider not only the quality domain, but also the spatial domain on what tiles to fetch, which will affect the video quality. And also, regardless of the underlying video encoding decoding technology, in Flare, we need to address issues such as how many hardware decoders we will use on mobile devices and how to enable the smooth video playback when viewers change the viewport. So next, I will focus on the viewport prediction, and you can refer to our paper for details on rate adaptation and video encoding. When talking about viewport prediction, I think the first question you may have is whether the viewport is predictable. So if the viewers change the head like this cute baby, it's nearly impossible to predict where they will watch next. So these two figures show the heat map of two sample videos using the data we collected during our user study. The heat map basically shows the viewing popularity of different areas within a video. And in the heat map, the x and the y-axis are the longitude and the latitude. As you can see from these two figures, there are focused areas in each of the heat map, which means that it's possible to predict the future viewport. Given that the viewport is predictable, the next question is how to predict it. We can roughly divide the method into two categories. For the short-term prediction, we can leverage classical models such as linear regression. For example, after collecting the head movement data during the history window, we can train a linear regression model and then use this model to predict the future viewport. But for the long-term prediction, the underlying data may not fit well into the regression model, so we are currently investigating deep learning models such as long short-term memory. Before presenting the accuracy on the prediction, I will briefly introduce our user study. In total, we collect the data for more than 4,000 minutes of video playback. We use 10 4K videos from YouTube, and we have 133 participants, and among them, 130 contributed validated data. And we build a player on Samsung Galaxy S8, and we use it with Gear VR to collect the data. For the prediction accuracy, we evaluate 4 different methods: static, linear regression, rigid regression, and support vector regression. For static, we assume that there will be no head movement during the prediction window. And we evaluate the accuracy for 3 different windows: 0.2 seconds, 0.5 seconds, and 1 second. And in these 3 figures, we show the CDF of the prediction accuracy. We see that a prediction is accurate if the predicted tile set is exactly the same as the ground truth. First, when the prediction window is 0.2 seconds, as you can see, the prediction is fairly accurate, and the linear regression performs the best. When we increase the prediction window to 0.5 seconds, the accuracy drops, and the rigid regression performs closely with linear regression. When we further increase the prediction window to 1 second, the accuracy decreases again, and at this time, rigid regression outperforms linear regression. So the takeaway is that the prediction accuracy depends on the prediction window with a short prediction window resulting in a more accurate prediction. So in Flare, we propose adaptive solution that use different models for different window. And also at a given time instance, we perform multiple predictions for different prediction windows, and we keep upgrading the prediction as time goes on. This figure shows the overall architecture of Flare. Because the prediction is accurate for short prediction window, Flare needs to perform the prediction frequently, which needs a lightweight solution. So we use a combination of linear regression and rigid regression in our current design. In the download planner, we decouple the tile scheduler and the rate adaptation to reduce the complexity of the formulated optimization problem. So our tile scheduler fetches not only viewport tiles, but also out-of-sight tells with a lower probability. When designing rate adaptation algorithms, we consider various QE metrics, such as the video quality, the store time, and the quality switch. After the player fetches the tells, so we have a decoding scheduler to leverage multiple hardware decoders to make the tells available to the system as early as possible. And also, in order to enable the smooth playback when viewers change the viewport, we decouple the decoding of the tells from the playback, and also we have a decoded tell buffer to catch the tells for a short period of time. And finally, on the server side, we have several optimizations to adapt to head movement and to enable a high-performance content delivery. So we have, in order to evaluate the performance of Flare, we implement Android player with C++ and Java. So, and also on the server side, we modify the Linux kernel to bypass the TCP send buffer to enable a priority-based tell delivery. For the experimental setup, we use 6 out of 10 videos and head movement traces for 11 out of 130 users. And we use both emulated Wi-Fi network with real-world bandwidth traces and LTE network for the performance evaluation. We compare the performance of Flare with 4 different algorithms. Festive and BBA are 2 viewport agnostic solutions, and Foo and H2 are 2 viewport adaptive solutions published last year. For Foo, basically it fetches the tells not overlapping with the viewport with the lowest quality, and the viewport tells with the highest possible quality under the constraint of the estimated bandwidth. So H2 enhances Foo by using the remaining network capacity to increase the quality of tells adjacent to the viewport. So I will first present the result on the user perceived quality. So we encoded the videos into 5 different qualities from 0 to 4, the higher the better. And on the x-axis, we show 5 different schemes: F for Flare, E for Festive, B for BBA, so U for Foo, and H for H2. We have 3 segmentation schemes: 4x6 with 24 tells, 4x4 with 16 tells, and 2x4 with 8 tells. And these results are for emulated network. So for the box plot, we show the mean, the median, the max, the 5 and the 95% tells for over 600 runs. So as we can see, for Flare, fine granularity segmentation can reduce the wasted network bandwidth, which result in a higher quality. And Flare outperforms H2 and Foo and performs much better than viewport agnostic solution. Next, I will present a result on stall. Stall is also known as rebuffering, which happens when the playback buffer is empty for regular video streaming. And here, as we can see, for Flare, the stall time per minute, the median is less than 1 second. So for FAST and BBA, there's almost no stall. And also for Flare, the stall happens when not due to the empty buffer, but because of the missing tells at the boundary. The interesting result is on the stall time for the other 2. As you can see, it's very high, especially for the 4x6 segmentation. The reason is that when decoding the 24 tells on mobile phones without a decoding scheduler like what we do in Flare, the decoding time could be very high. And in terms of network efficiency, we use a metric called user perceived ratio, which is the ratio between the displayed data and the downloaded data. As we can see, for Flare, fine granularity segmentation can result in a high perceived ratio, which is around 0.35, much higher than the 0.15 perceived ratio for FASTIV and BBA. So the takeaway message is that Flare can significantly improve the quality of user experience and network efficiency. We have the results for other experiments in the paper, for example, the results on LTE network and the results for energy consumption. We also tested a few 8K videos. You can find the results in our paper. So to conclude, In this work, we present a Flare Viewport adaptive 360-degree video streaming system for mobile devices. And the Flare leverages machine learning-based viewport prediction to increase the video quality with less data, which is demonstrated by our extensive performance evaluation. And we are currently investigating deep learning-based viewport prediction method and also the offloading of the video decoding from the mobile device to the mobile ad cloud. And we are also looking into emerging media such as volumetric video streaming. This is the end of my talk. Thank you for your time. We have a lab demo in the evening. Please come by. Thank you.
Our next talk comes from Mi Zhang from Michigan State University. He's a professor there, and his student is B.E. Fang, and so this is their work together. Are we projecting? Their work is NestDNN. It's a resource-aware, multi-tenant on-device deep learning for continuous mobile vision. Take it away.
Hello, everybody. My name is Mi Zhang. I'm assistant professor at Michigan State University. This work is a joint work with my students, B.E. Fang and Xiaozheng. Unfortunately, due to visa issues, they can't be here. So although I'm the presenter of this paper, most of the credits belong to both of them. So let's get started. So mobile systems with onboard video cameras, such as smartphones, drones, AR and VR headsets, are revolutionizing our lives now. These modern mobile vision systems share two key characteristics. First, they usually run multiple applications concurrently. Sorry, it just doesn't work. Okay. So these modern mobile vision systems share two key characteristics. First, they usually run multiple applications concurrently, each targeting a different vision task. Second, the number and the types of vision tasks can be changed depending on the current context. For example, a AR headset that is able to not only recognize the object the user is interacting with, but is also able to understand the scene the user is surrounding with. When the user is interacting with anybody, the AR headset is able to recognize the person if possible, as well as his facial expression. So in the past few years, deep learning has become the dominant approach in computer vision due to its capability of achieving impressively high accuracies on a variety of vision tasks. As the deep learning chipsets emerge, there is a significant interest in leveraging this on-device compute resources to execute deep learning models on mobile systems without cloud support. So unfortunately, deep learning models are known to be resource demanding. To enable on-device deep learning, one common approach used by application developers is to compress the deep learning model to reduce its resource demand, normally at a modest loss in accuracy as a trade-off. Although this approach has been successfully applied to developing a variety of state-of-the-art mobile deep learning systems, it has a key drawback. Since the application developers develop their applications independently, the resource accuracy trade-off of the compressed model is predetermined based on assumed static resource budget at the application develop stage. And this resource accuracy trade-off is then fixed after the application is deployed. However, the available resources in the mobile vision systems at runtime are always dynamic due to events such as starting new applications or closing existing applications. As a consequence, when the available resources could not meet the demand of the deep learning models, resource contention occurs, forcing the streaming video streams to be processed at a much lower frame rate. On the contrary, when the extra resources available, the compressed model could not utilize these extra available resources to regain its sacrificed accuracy back. So, in this work, we present a novel framework named NestDNN that enables resource-aware multi-tenant on-device deep learning for mobile vision systems. As an overview, NestDNN is able to dynamically select the optimal resource accuracy trade-off for each deep learning model at runtime to adapt the model's resource demand to the system's available runtime resources. The design of NestDNN involves two key technical challenges. Firstly, if you recall, the limitation of existing approach is rooted in the constraint where the resource accuracy trade-off of a compressed deep learning model is fixed. Therefore, the first challenge lies in the designing a scheme that enables the deep learning model to provide flexible resource accuracy trade-off. To achieve this goal, one natural idea is to design multiple compressed models with various resource accuracy trade-offs and have all of them installed in the mobile system. However, this is not a scalable solution. This approach becomes infeasible when the number of vision tasks or the number of compressed models for each task increases. The second key challenge lies at the fact that selecting which resource accuracy trade-off for each of the concurrent running applications is actually not trivial. This is because different applications may have very different goals on accuracies and processing latencies. Taking the traffic surveillance drone as an example, an application that identifies plate numbers normally requires very high accuracy but does not need a real-time response. On the contrary, another application that counts vehicles to detect traffic jam does not need very high accuracy, but requires very low latency. So, to this end, to address the first challenge, NestDNN incorporates an innovative model pruning and recovery scheme that transforms a deep learning model into a single, compact, multi-capacity model. The multi-capacity model is compressed of a set of descendant models, each of which offers a unique resource accuracy trade-off. However, these descendant models are actually not independent. The descendant model with smaller capacity share its model parameters with the descendant model with larger capacity, making itself nested inside the larger one without taking extra memory space. This is actually where the name comes from. In doing so, the multi-capacity model is able to provide various accuracy resource trade-offs within a very compact memory footprint. To address the second challenge, NestDNN encodes the inference accuracy and processing latency of each descendant model into a cost function. As you can see here, the A-mean V represents the minimum inference accuracy goal set for the application V. The L-max V represents the maximum processing latency goal set for the application V. And UV is the compute resource percentage allocated to application V during runtime. And alpha is the knob set by the user to determine the latency accuracy trade-off preferences. In a higher level, the cost function penalizes the descendant model that achieves lower accuracy than A-mean and has a much larger latency than L-max. Given all the cost functions, NestDNN employs a resource-aware scheduler, which incorporates two widely used scheduling schemes to jointly maximize the performance of concurrent applications for two different optimization objectives. The first scheduling scheme, named mean total cost, aims to minimize the total cost of all the concurrent applications. Under this scheme, the scheduler favors applications with lower cost, and therefore is optimized to allocate more runtime resources to all of them. The second scheme, named mean max cost, aims to minimize the cost of the application that has the highest cost. Under this scheme, the resource-aware scheduler is optimized to fairly allocate runtime resources to all the concurrent running applications to balance their performance. To evaluate the performance of NestDNN, we use the resource-agnostic approach, which uses a fixed resource accuracy trade-off as our baseline. As you can see here, the yellow circle represents the runtime performance of our resource-agnostic approach. Each blue diamond marker represents the inference performance, runtime performance of NestDNN with a particular alpha. As you can see here, the horizontal and the vertical dotted lines altogether partition the whole figure into 4 quadrants. The upper right quadrant represents a region where NestDNN achieves both better accuracy and frame rate compared to our baseline. In short, under 2 different scheduling schemes, NestDNN achieves as much as 4.2% increase in inference accuracy, as well as 2.0 times increase in video frame processing rate compared to the baseline. To conclude, in this talk, we presented NestDNN framework that enables resource-aware multi-tenant on-device deep learning for mobile vision systems. So the key idea of NestDNN is to generate a multi-capacity model that provides flexible resource accuracy trade-offs, and to dynamically select the optimum one for each of the concurrently running deep learning models to jointly maximize their performance. To that end, we believe NestDNN represents a significant step towards turning the envisioned continuous mobile vision into reality. Thank you.
Our next talk is from Wangwei Xu from Peking University. And this is a collaborative work with Peking University, Microsoft Research, and Purdue University. And they'll be talking to us about deep cache, a principled cache for mobile deep vision. Take it away.
Thank you, Robert, for your introduction. Hello, everyone. I'm Wangwei Xu from Peking University. I'm honored to present our work, Deep Cache, Principled Cache for Mobile Deep Vision. It's a joint work with Microsoft Research and Purdue University. So as last speaker already mentioned, mobile vision have been popular on mobile devices. A lot of interesting and exciting mobile vision applications have emerged, such as augmented reality and face detection. So the core technique of those applications is the computer vision algorithm. So as you know, the state-of-the-art algorithm for many computer vision tasks is the convolutional neural network. A CNN model is typically comprised of a lot of computation nodes or layers belonging to different types such as convolution, pooling, and activation. So although CNN has been proven to be very accurate, it's also known to be very resource hungry. Running such algorithm on mobile devices may result in unacceptable long user perceived latency and quick battery drain. A lot of prior efforts have been trying to reduce the workloads of on-device deep learning. Most of them target at the algorithm level or hardware level, such as model compression and designing neural net specific processors. In this work, we propose to reduce the workloads of CNN models by leveraging the temporal locality of mobile video streaming, which means the images sequentially captured by a mobile camera often have substantial similar regions that we can reuse. But notice that although those images look similar, they are not actually identical due to some scene variations such as object movement and camera movement. So let's first look at a naive approach. Without cache, an image will be first fed into an inference engine. The engine will process the image based on a given CNN model, and we will have the output. To enable a cache policy, we can first match the current frame to the previous one. If the similarity is larger than a threshold, we can skip all the CNN computations and directly reuse the output from the last frame. Otherwise, we run the whole deep learning pipeline without reusing any computation results. We deem such approach as too coarse-grained because it treats the whole image as a basic unit for comparison. As a result, the decision about reusing is all or nothing. And also, such approach cannot handle tasks whose output is position sensitive. For example, if two images have similar background, they tend to be identified as reusable. However, the objects inside between the two image frames may move a little bit. Such movement will not be able to be captured by this naive approach. So the key idea of our approach is to reuse the CNN computation results of only those similar regions at a fine-grained layer level. In such a way, we can reduce part of those computations, but also maintain the model accuracy. So in this work, we propose a fine-grained cache system, which we call deep cache. It works as follows. When a new image comes, it will be first matched to the previous one based on our novel image matching algorithm. The algorithm will accurately and fastly identify the reusable regions among those two images and pass it to our revised inference engine. The engine will propagate the information about those reusable regions among different CNN layers and reuse the computations from the last frame. And finally, we will have the rightful results which can be different from the last frame. There are some challenges for the proposed cache design. For example, the scene variation on the real-world environments can be complicated. The background may move between two sequential images, which means we should not only match the image blocks at the same position. We also notice that the reusability tends to diminish at deeper layers during the model inference. This is because, for example, during convolutional layers, when the filters or the kernels travel to the border of the import feature map, the corresponding result as the output feature map will become not reusable. We call such phenomenon as cache erosion. So as you can imagine, after several layers of cache erosion, the size of the reusable regions may become zero, and we will have nothing to reuse. To battle with cache erosion and maximize the reusability during the inference, our solution is to try to merge the reusable blocks to be larger ones as much as possible. We also have a good news here that after characterizing the workloads of typical CNN models, we find that the early layers of those models often contribute to most of the computations, and those early layers, of course, suffer less from the cache erosion. Here is an overview of our system. We designed the system to require no cloud offloading or any program efforts from developers, and it can work with off-the-shelf deep learning model without any modification. The system contains two main models. The first one is the image matching algorithm, which runs at the very beginning to identify the reusable regions among two images. And the second one is a cache-aware inference engine, which carries out the real deep learning workloads. So the image matching algorithm takes two raw images as input and output a set of reusable regions in the shape of rectangles. We also want the reusable regions to be able to be merged as large as possible to reduce the suffering from the cache erosion. So as the first step, we divide the current image frame into smaller blocks. The size of the block is a configured number with a default number as 10 by 10. Then we find, for each block in the current frame, we find the most matched block in previous frame with the highest similarity. So this is a classic usage of motion estimation algorithms, which is widely used in video compression. Here we empirically choose diamond search as an algorithm to identify the most matched block. Then we calculate the average movement between each block in current frame and the corresponding most matched block in the previous frame. This average movement can be regarded as the movement of the whole image. We then calculate similarity between each block in current frame and the corresponding block with the average movement we just calculated in previous frame. If the similarity we calculate is larger than a threshold, we treat those two blocks as reusable. Here we use peak signal to noise ratio as the metric to measure similarity. And also the threshold used here is configurable with a default number as 20. So finally, we merge the reusable regions into larger ones because the offset of each block we just matched has the same offset, which is the average movement of the whole image. So such mergence is feasible. Here we further use two ways to reduce the overhead of the image matching algorithm we just discussed. First, in the second step, we don't need to find the most match block for each block in current frame. We just want to estimate the average movement of the whole image, so we can skip some of those blocks to reduce the workloads. Our experiments show that we can actually skip more than 70% of those blocks, but still obtain the correct average movement of the image. And second, in the fourth step, some similarities between the current frame and the previous frame have been already calculated in second step, so we can reuse the computation results as well. So after the image matching algorithm, the information about the reusable regions will be passed into our inference engine. However, remember that the size of the reusable regions are not unchanged. It will shrink during inference for the reason of cache erosion. But the impacts from different layer types on those reusable regions are different. Here, we classify those layer types into three main categories based on how they affect the reusability. First, the convolutional and pooling layers will reduce the size of the reusable region. Second, the fully connected layer will totally destroy the reusability because it connects each output neuron to each input neuron. Finally, some other layers, such as activation layers, have no impact on the reusability because it only connects each output neuron to one single corresponding input neuron. So based on the observation into how those layers are implemented, we can correctly adjust the reusable regions during the model inference. So here's the question, why we want the propagation? Why not just match the import feature map at each CN layer so that we know exactly which regions we can reuse? Such approach may work, but it's not very practical because first, the feature maps are very high dimensional data which we have very few knowledge to interpret. As a result, it will require a lot of effort from the model developers to empirically determine a threshold for each CN layer. And second, matching the feature maps for each layer require a lot more computations than matching only the raw images. The overhead actually can be 40 times more, as demonstrated in our experiments. So after knowing which regions are reusable, we can directly copy the results and skip the computations. Here we only reuse the computations of convolution layers because they are the dominant layer. Second, we also carefully implement our reuse process so that the data locality will not be hurt. We implement our image matching algorithm based on random script, which supports GPU acceleration. We implement our cache-aware inference engine based on a very popular deep learning inference framework for mobile devices. So we evaluate our system based on 5 typical CN models and 2 large-scale datasets. The experiments are carried out on a Nexus 6 device with Android 6 installed. We also compare our system to the original NCN framework without any cache, and also a priori work which implements a coarse-grained cache mechanism. So in overall, deep cache can save around 15% to 28% model execution time on average. Such saving, of course, depends on the concrete model architectures. For example, deep cache performs better on shallow models such as AlexNet than deeper ones. This is because, as also demonstrated in our experiments, going deeper means the reusability is reduced, so we will have less computations to reuse. Deep cache can also save around 20% energy consumption when processing the same number of images compared to no cache framework. Such energy saving is actually significant considering that the mobile vision applications are very energy hungry. For example, the saved energy for use deep cache to process 10 images is enough to support 40 seconds of video playing on our experimental device. So because deep cache reuse the computations of those regions that are not actually identical, the model accuracy can be compromised. However, according to our experiments, the model accuracy drop is actually very trivial, about 2% on average. This is because we carefully design our image matching algorithm to reuse only those very similar regions, and we use a very conservative propagation approach to make sure that the reusable regions are never force expanded during the model inference. Finally, we measure the overhead of memory overhead for the need of cache. The results show that the memory overhead is no more than 44 megabytes, which even for very large CN models, this is because we only cache the results of convolution layers and we only keep the cache for one single image frame. To summarize, we designed and implement a cache system for mobile vision applications. As evaluated, the system can effectively reduce the execution time and the energy consumption with very few accuracy loss. Thanks for your attention.